Bismillahirrahmanirrahim. Today we are going to talk about the uniform circular motion. In our previous lectures, we were talking about the velocity with the acceleration, the displacement, all of them were linear. But today we will talk about the circular motion, the uniform circular motion. So the uniform circular circle. So we have, there must be something about a circle in this case. We also have the motion here and uniform. So uniform, when we were talking about for example uniform velocity, uniform means that it's not changing. What is not changing here is the terminal velocity. So the terminal velocity is not, the terminal speed is not changing. It means that if, for example, we have a circle also has a radius. So this has a radius and we have something is moving in a circle. So we have a mass m. So that's moving in a circular path. For example, this is the speed of this object is 15 meters per second, and throughout this trajectory the speed will remain the same. That's why this is called uniform circular motion. So this object is moving with the uniform speed. The value of the speed is the same and it's not changing with the time. That's why it is called the circular motion. What is actually changing is the velocity. So velocity has a direction. So at the one moment in time, the velocity direction is here, but if the object is here, then the tangential velocity here is that's the velocity. If the object is here, then the velocity direction is this one. So we can see that the velocity is changing, but the speed is the same. So since the speed is the same, that's why this type of motion is called as the uniform circular motion. So the uniform is for the speed that is not changing. And now we talk about the terms that are related to the uniform circular motion. Some terms. The first thing is the time period. The time period is the time that this object takes to complete one rotation. So that time is called the time period. So when the object starts from, for example, here, it completes one rotation, that's called the time period. So time period is represented by t. So we have a time period, that's big T, and it's given in seconds. So seconds is the unit of the time period. So it's a standard SI units. The second term that we need to understand is the frequency. Frequency is that how many times this object is completing one rotation in 1 second. So the other one is frequency. Frequency. And it's represented by F. So it's the number of rotation per 1 second. And we can see here we have numbers. Number of rotation doesn't have a unit, but second has a unit. That's a time. So we all have its unit is 1 or second, or it can, we also use the standard is the hertz. So hertz is the unit of the frequency and it's equal to 1 or second. So the frequency is the time that is required, and the frequency is that in 1 second how many revolutions are completed. And then the relation between the frequency and the period is, it has an inverse relation. So again we can see here, so frequency has a unit 1 over second, and here we have 1 over second, and we have 1 over t here, and this is the time period. And now since we are talking about the circular motion, so everything will be circular here. Means that the velocity that we talked about in our previous lectures was the linear velocity. That means that everything was moving in either a straight path or it was not a circular path. But here we will talk about the circular velocity. In the linear motion, so for example, when we were talking about a linear motion, for example, we have a car that's moving from point A to point B. So we have a displacement that was given by x, or for example, in centimeter, this is 1 centimeter or 1 meter. But we were talking about a distance. We were able to measure. We can measure that distance with the meter rod, for example, or with the other instruments. But it's a straight line. In the case of the angular or the circular motion, what's actually changing is not this distance, but for example, that's the changing thing is the angle. For example, right now, if the object is here, this is, for example, the x-axis. With respect to x, the angle here is 0. But if the object is here, then it's making, with respect to x, that's the angle that is changing. So we have the theta that is changing. For example, when the object is here, then the angle is 90 degrees. So what's changing here is the angle. So that's why when we talk about the uniform circular motion, for the displacement, we use the angular displacement. So for example, we have 3D plane and we have, so this is a circle, and this is y, this is x, and this is z. So when we talked about this thing earlier, that we always take the angle with respect to the x-axis. So if something is moving, so this is the angle. For example, an object is here, then we take this angle. So this is the theta. But if the object is moving, of one point is this is point A, another point is, for example, is here, point 2, and then the difference between these two is delta theta. So we always, when we talk about the uniform circular motion, then we take the angular displacement. And for the angular displacement, we take the delta theta. And delta theta is the angle between the point 1 and point 2. So this is how we define the angular displacement. And now the unit of the angular displacement, we already know this is the angle. So angle can be represented in degrees. Degrees is by the convention. We have, for example, a circle. When we have a parallel straight line, this straight line here, this is 180 degrees, and then if we divide this by 2, we have a perpendicular line, then this is 90 degrees, and the complete circle is the 360 degrees. So this is the one unit. The degrees are the one units that is also used in some books. And the other unit is the how many revolutions. It's also revolutions is also a unit that's used for this angle, the angular displacement. Revolution means that, for example, we have an object that starts its motion from here, and when it completes the one rotation, we can say that the 360 degrees is equal to one rotation, and 180 degrees is 1.5 rotation. And we have here, for example, if the object is moving from here to here, then it's the 1/4 of the complete rotation. But the standard unit that is used is the radian. That's the SI unit. So we have the theta for the so for example, we have this distance. The distance between these two is S. So then the theta is defined by S by R, or S equals theta by theta into R. So this is how we define the angular displacement in terms of the distance and the radius. But now we want to know what is the 1 radian, and for that we know that the theta is equal to S by R, and for the complete circle, we know that the circumference, the length of the outer part of the circle is 2 pi r divided by r. So this is, we know, is the that cancels, the r cancels with each other. So for the complete circle, we know that the angle in terms of radian is 2 pi r radian. So for the complete circle, we know that we have 2 pi, so 1 pi is the 180 degrees and 2 pi is then 360 degrees. But now this is for the complete circle, we want to know what is 1 radian. So for the 1 revolution, so for the 1 revolution, so we just saw that we have 2 pi radian, and this is equal to 360 degrees in terms of degrees. So this is in radians. In radians, the complete circle is 2 pi radians, and in terms of degrees, we have 360 degrees. So 1 radian then. So 1 radian is equal to 360 degrees divided by 2 pi, and that is equal to 57.3 degrees. So this is how we define the 1 radian. So for the 1 complete circle, we have 360 degrees in terms of the degrees when we use the unit degrees, and for in the radians we have 2 pi, but 1 radian is equal to 57.3 degrees. So we talked about the angular displacement, and similarly when we talked about the linear motion, we were talking about also the linear velocity, but here we will talk about the angular velocity. So angular velocity. So the angular velocity is represented by omega, and this is same as the linear velocity, but here we will use the theta, which is the angular displacement divided by time. So the time rate of change of the angular displacement is known as the angular velocity, and we know that for the complete circle, that means that the complete circle, as we said, that complete circle has in terms of radians we have 2 pi, and when the complete circle is 2 pi, and we also said that to complete how much time it takes to complete our circle or the complete 1 rotation is known as the time period. So divided by, so this time we can write t here. And now we want to know what is the relation between the angular speed or the angular velocity and the linear velocity. We know that the linear velocity was represented by only t, only the simple v. So for the complete circumference means the length of the complete circumference is the 2 pi r divided by t, but we know that 2 pi by t, so 2 pi by t is equal to omega, so we have omega r. So we have the velocity is equal to omega r. So this is the relation between the linear velocity and the angular velocity here in this case. And now since we know, we see that, so now we see that the tangential velocity means, as we just said, that here in this case the velocity direction is here, and here when the object is here the velocity direction is here. So we see that there is the change in the velocity, the direction, not the magnitude, because this is the uniform circular motion. The magnitude of the velocity is the speed, and the speed is same in this case. That's why this is known as the uniform circular motion. But we see here that there is a direction of the velocity that is changing. So if the direction is changing, that means the velocity is changing. So there must be something in this direction that is causing this change, and that's known as the acceleration. So this is the acceleration. So there is the constant acceleration that's towards the center of the circle, and that is causing this change in the velocity, and that's our angular or it is also known as the centripetal acceleration. So that's the centripetal acceleration. Centripetal acceleration is that acceleration that is causing this change in velocity to keep this object in a circular path. That is called the centripetal acceleration, and this centripetal acceleration is given by the v square divided by r, and in terms of omega, the angular velocity, it's given like this. So this is the centripetal acceleration. And now we take one example, and that's the vacuum cleaner. So the vacuum cleaner has a motor which is spinning very fast, and that's how the vacuum cleaner is working. And right now we want to know what is the angular acceleration, and what is the linear acceleration in that case, and what is the angular speed that we just discussed. So for example, the radius of this motor that's spinning in the vacuum cleaner is 10 centimeter. So it's this size. For example, we have a small or medium sized vacuum cleaner, and we want to see that how much acceleration is there. So, and the motor that is spinning inside the vacuum cleaner is the speed, the angular speed is 600 RPM. RPM means revolutions per minute. This is another commonly used the unit for the angular speed, which is not the SI unit, but it is commonly used. That means the revolutions, how many revolutions are there per minute. So, and the frequency here is 10 hertz. That means in 1 second it is spinning 10 times. So the time period we know that is 1 by 10. So it's a frequency inverse relation. So this is Hz. And this is in terms of seconds. So for the angular speed or angular velocity, we know that we have the 2 pi by t. So if we put this value here, we know pi is a constant value, so we will get a 63 radians per second. So this is the angular speed, angular velocity of that the motor that is spinning in the vacuum cleaner. And right now we want to know what is the linear velocity, and we know that the linear velocity, we just derived this relation. So we put this value, we have the omega here and we have the radius here. So if we put these values, then we will have the 6.3 meters per second. And now we want to know what is the acceleration, the centripetal acceleration, and we also derived this relation. So it was r, and it's also equals to VR divided by v squared divided by r. So we have v here, we have r, and we also have omega. Omega is here, and we have r. So we can easily, if we put these values there, we can calculate it. So we have the 400 meters per second squared. So this 400 meters per second squared is very high. It is very high acceleration. If we compare it to the acceleration due to, so if we compare this to the acceleration due to the gravity, so the g that we talked about in our previous lecture was 9.8 meters per second squared, or we can also say that 10 meters per second squared. If we compare it to this one, this is much higher. That's why the acceleration is so high. That's why the vacuum cleaner is sucking everything in. That's why it's dominant when we turn on the vacuum cleaner. The vacuum cleaner, the air is so moving very fast. The acceleration is so high that the acceleration, this acceleration is dominating the gravitational acceleration. So this is very high value. So now we know that why is the everything sucking in, even if we have a gravity there. Now, since we talked about the angular velocity and we also talked about the angular acceleration, so we have a circular motion. So we have a circular motion. So we have a circle. So we have a circle, something, a mass m is moving in a circular path. So that means that we just said that there is a acceleration which is in the direction of the central direction. We have the center here, we have a radius here, so we have a tangential velocity is changing. That means that there is an acceleration. We just discussed about it, and it is known as the centripetal acceleration. So at each and every point this is changing, so we have this acceleration. And now we know that from the Newton's second law of motion, if there is an acceleration, so we have the F equals ma. So we have a or ma, so we can commonly known as ma. So if we have an acceleration, if a mass is accelerated, that means there is some force that is causing this acceleration, and this force is known as the centripetal force. So imagine, so to give you some idea that how is there a force if something is moving in a circular path. Imagine there is a table. There is a table that is moving with that has some angular speed, and you are, so this is the center, and you are sitting on a table. So and you are sitting on a table, and you will feel a force, if there is nothing, if there is a table that is spinning and there is nothing that you are holding, and so if this is spinning, you will feel a force, you will move away from the center. But if there is a chair, for example, if you are sitting on a chair and this is spinning, so the chair, you are on a chair and this chair is spinning, so you will feel a push from your back, and that chair, you will feel that the chair is always pushing you towards the center, and that force is known as the centripetal force. Now imagine that there is no chair there, but you are here, you are for example here, but there is a rod. You are holding that rod. So this spinning, this chair, this table is still spinning. Now you will feel a pull, that the rod is actually pulling you towards the center if you are spinning. If for example you have a string and there is a stone attached to it, if you try to spin it, you will feel a force, and that will be towards the center of this motion, and that force is known as the centripetal force. And this force, centripetal force, so we write a small c, it's because of the centripetal force. So we are talking about the centripetal force. So the centripetal force is that force that keeps the object in a circular path. So it was we also talked about the acceleration, but if there is an acceleration, there must be a force. So the centripetal force is that force that keeps the object to move in a circular path, and it is given. So we have the F of c is equal to ma. This is the Newton's second law, and it is given by m v squared divided by r, if we put the same value from there. And in terms of omega, which is the angular velocity, is m r omega square, and it is always towards the center. We have, for example, this is a center, so the centripetal force will be in this direction, and the tangential velocity will be here. So that's why there is a constant force. That's why the tangential velocity is changing. And now to explain this centripetal force, we are taking one example. An example is that a 100 kg car, which is a normal, usually a small or medium-sized car, is turning around in a corner at the speed of 10 meters per second as it travels along an arc of a circle. That means that there is a road that is curved. Means there is a road that is curved, and there is a car that is moving in this curved path, and it is moving, so it is moving with the velocity, the tangential velocity is 10 meters per second, and the radius of this curve, for example, there is a center, so this radius is equal to 10 meters. So this circular path, there is a curve, and there is a car that is moving in a circular path. And so how large is the road, how large a force must be exerted to keep a car in a circular path? Since we know that if the car is moving, or any object that is moving in a circular path, there must be a force towards the center, and that is known as the centripetal force. So we are asked if the radius of this curve is 10 meters and it is moving with the 10 meters per second. So what is that force that is causing this acceleration? Because the tangential velocity is tangential velocity is changing, and this force is actually coming from the tires, that is the frictional force. The frictional force is actually causing this centripetal force, which is in direction of the center. So we know that, say, same relation, we have Fc, we have M, we have, so the mass here, is the mass is equal to 1000 kilograms. So we have a mass v squared divided by r. This is the centripetal acceleration, centripetal force. If we put this values 1000, this is 1000 multiplied by, so this is 10 squared divided by 10, we have 10 meters. So this force is equal to 10 raised to the power 4 newtons. So we need 10,000 Newton force, 10,000 Newton force to move the car in a circular path, and which has a radius of 10 meters and its velocity is 10 meters per second. So this is the example for the centripetal centripetal force. Now, since we talked about the centripetal force and the circular motion, and now we take another example, one interesting example. For example, we have a test tube. So we have a test tube, and there is, you know that this is a container that is usually used in laboratories. And we have a marble here. We have a marble here. And this is moving like this. So we have a marble which is rotating like this. So we have a test tube which is rotating. For example, my hand is a test tube, so it's the same test tube, and it is rotating like this. So it is spinning like this with the angular speed omega. And we want to know what will happen to this marble if there is nothing to stop this marble. So the marble is here, it can move freely in this test tube. So if we rotate this marble, this test tube, and so at the next moment in time, this test tube will be here. And the next moment in time, this test tube, so this is the marble. So this is the marble here, and the next moment in time, so this test tube will be here, and the next moment in time, this test tube will be here. So we can see here the marble will move towards its edge, so like this. So when we rotate the marble, the test tube, the marble will try to move towards the edge of this test tube, and that is because that the marble there is nothing to stop it, and there is no force, nothing is pushing them, and the marble will try to keep or to resist this change in motion. That's why it will move towards the edge of this test tube, and when it reaches the edge of this test tube, and then the edge, we can see here it's closed, so it will then stop it, and then it will cause a centripetal acceleration and force. So this is centripetal force. But if there is nothing here in this case, for example, initially, so it will go towards the edge, but since we are rotating, so we in this case, so when it was here, so it was going towards the edge of the test tube. So this is the concept behind the centrifugal force. So the centrifugal force, centrifugal force. So centrifugal force is the force that is opposite of the centripetal force. So the centripetal force, we can see here, it's causing the object to move towards its center, or the direction is central. But the centrifugal force, we can see here, when we were trying to rotate in the circular path, the object was moving towards the edge. If this is moving towards the edge, that means there is a force, and that force is known as the centrifugal force. And this is the same concept that is used, the same basic physics concept that is used in the drawing machine. A drawing machine means when you dry the clothes. So we have, for example, this is a So the drying machine, it has a drum, so it has something like this, and it is spinning like this with the omega. And when it is spinning, but it has small holes, you see the water, since it is spinning like this, the water will try to go towards the edges. In this case, since there was something solid there, the marble was stopped, and there was a centripetal force that was keeping this object in a circular path. But here, in this case, when in the drying machine, when this drum is spinning, but the water is always going towards the edges. But here there are holes. Since there are holes in these drums, the water can leak out, and then this is how you dry your clothes after washing it.